What's going on, guys? Welcome back to the channel. Today we're going to be going through integration by parts and also trigonometric integrals and exactly how to go about solving it, because I've already put up a integration by parts video. If you haven't already, make sure to check that out. I'll put that link in the description. But essentially this is going to be about how to answer those hard ones and a method almost of how to approach these kinds of questions formulaically, so that you've kind of got a strategy whenever going into these types of questions and you're not thinking blind. So without further ado, guys, let's get right into it. Right, so the first thing to recognize is obviously that with integration by parts, okay, our formula is the integral of u dv is equal to uv minus the integral of v du, okay? That's standard, we know that. Now, with that, what are the common pitfalls, okay? And how do we choose u? The key thing here, okay, is to remember a acronym called LI8. Okay, so it's logarithms, inverse trig functions, and algebraic functions, and then normal trig functions, and then exponential functions at the bottom. You could probably guess what this acronym is for, and it's actually you use it to choose u. Okay, so why does this work? Well, this works because, remember, for dv, okay, we have to be able to integrate it. Okay, and so when we're picking dv by dx, this is obviously going to be the best one. Exponential functions is the easiest. And meanwhile, you know, integrating logarithms and inverse trig functions, it's not as simple as these, right? And so we go about choosing u according to this acronym, okay, LI8, in order to effectively guide us to make sure that we're not thinking too much about, you know, what exactly to do. When we get the question, we can kind of just use this and spot it. It's not perfect, but it works in most cases. And it helps us to choose u. So if you can't do logarithms as u, you'll go for inverse trig. If you can't use inverse trig as u, then you go for algebraic, etc. So it's in this order. Alright, so just to illustrate a quick example, guys, what we've got here is the integral of ln x over x cubed dx, okay? So what are we going to write this as? Well, we can simplify this down now, and we can say that this is going to equal the integral, okay, of x to the power of -3 times ln x dx, okay? Perfect. Okay, so now what we can say is, how does this pair up against our acronym? Right? How does this pair up? We need to pick u, right? So what is our value of u going to be? Our value of u here, according to this, is, well, look, we've got a logarithmic function, and we've also got a algebraic. Okay. Now the logarithmic function appears higher in the acronym, so therefore I'm going to say let u equal ln x, and let dv by dx equal x to the power of -3. Okay. Now we can say, well, that must mean that du is going to equal 1 over x dx, okay? And we can therefore say as well that dv is equal to x to the power of -3 dx, okay, which means that v is going to give us the value of x to the power of negative 3 at the integral of x to the power of negative 3 dx, which gives us negative a half x to the power of minus 2. Now, according to our formula for integration by parts, okay, we've got uv minus the integral of v du. So we're going to say, okay, we've got ln x u, we've got v negative a half x to the power minus 2, and minusing the integral of v du. Okay, so v, okay, and du, 1 over x dx. Okay, putting that all together, what do we get? Well, that's therefore going to equal minus a half x to the power minus 2. Okay, ln x, and plus the integral of a half, okay, x to the power minus 3 dx. Okay, which therefore gives minus a half x to the minus 2, okay, ln x, right, and then we're going to have the integral of this, so that's going to give us minus a quarter x minus 2 x, sorry, plus c. Okay, and we can just simplify this down now. So what does that give us? 1 at negative 1 over 2 x squared ln x minus 1 with 4x squared plus c. Okay, perfect. So that's going to be the answer for this question that we just solved using our LI8 acronym, and is a first introduction question to integration by parts. So here we've got another question, and it says find the integral of x squared times e to 3x dx. Okay, so let's go back to our acronym here. Let me get this in a different color for us. Let's put some red here. Okay, we got that again. So we've got an algebraic function, and we've also got a exponential function. So therefore, what we're going to do, we're going to say let u equal x squared. Okay, we're going to let u equal x squared. I'm going to say let dv by dx, okay, equal e to the 3x, right? Which therefore gives dv equal to e to the 3x dx, which gives v as obviously the integral of e to the 3x dx, which gives us a value of a third e to the 3x. Okay, and over here we can say that du is going to equal 2x dx. Okay, perfect, brilliant. So going back, remember, using uv minus v du, okay, we can say that from here we're going to get x squared to times a third e to the 3x minus the integral of a third e to the 3x, okay, 2x dx. Okay. Brilliant. And so we can just rewrite this now. We're going to get equals a third x squared e to the 3x, okay, minus 2 over 3 xe 3x dx. Now, as you can see, what we've ended up here with is another product, okay? Another product where we have to reapply integration by parts, okay? And this is very common, especially when we've got values, exponentials. So over here, we're going to say the same thing. Look at our anagram, lie 8. Okay, what comes first? Well, the algebraic functions, exponentials. So we say let u equal x. Okay. Therefore, we can say du is equal to dx. Then we're going to say let dv by dx, okay, equal e to the 3x. So dv is equal to e to the 3x dx, which therefore means that v is the integral of e to the 3x dx, which means that v, okay, is going to equal what? We actually put this here. Might as well do the whole thing. So 2 over 3. Whilst we're here. So we can say then this, if we integrate this, we're going to get a value of 2 over 9 e to 3x. Brilliant. Now with that, we can say, well, we've got our values here, right? So we've got uv, remember uv minus v du. What's that going to give us here? Well, we've got u, which is x. We've got v, which is 2 over 9 e to the 3x. Right, we've got an integral of v du, which is dx. Okay, so if we plug this back in, what do we get? We get this minus 2 over 9 xe to the 3x minus the integral of 2 over 9 e to the 3x dx. Alright. And so we can just move it from here. So we can say that we're going to get okay, which is therefore going to give us what? We're going to get a third x squared e to the 3x, okay, minus 2 over 9 xe 3x plus 2 over 27 e to the 3x plus c. Okay, so just a recap on that. Remember, according to our acronym, we just did, okay, cool. X squared is the algebraic function, okay, and e to the 3x is our is our exponential, so we're going to let u equal x squared. And then we just took it from there, okay, applying our uv minus v du, integral v du, and we then got stuck with another integral we had to solve, so we just did that. Okay, and we plugged it back in to get this final answer. Alright guys, so now we got a scenario where we've got the integral, okay, we've got integral of t to the power 3 times e to the t squared. Now according to our acronym, okay, we should say we'll let u equal t to the 3, okay, let dv by dx equal e to the t squared, okay, but then it should actually be, so it's dt, and then we get what? We get dv is e to the t squared dt. So then v is equal to the integral. But as you know, we can't evaluate this. So it doesn't work in this scenario. So what do we do? What do we do? Well, a few things to do. Okay, think about it. This is the same thing as saying t squared times t e t squared dt. Okay, and we can evaluate this. Okay, we can evaluate this. If we go let u equal t squared, okay, and then we say therefore du is going to equal 2t dt, right? And then we can also say let dv, okay, dv by dt equal t e t squared. Therefore I can say that dv is equal to t e t squared dt. So v is going to equal, okay, but now we can evaluate this. Why and how? Because we can apply some u substitution. Okay, so if I say let me just do a quick subtitle. Okay, so if I say let u equal t squared here, say u1, I therefore get what? Well, if I let u1 equal t squared, okay, then du1 is equal to 2t, okay, dt, and so from here I can then say, okay, well a half of du1 is equal to t dt. Okay, and so from that I can say, well, according to this, we've got the following. We've got the integral of half, okay, half du1 times e to the u1, right? So we get a half of the integral of e to the u1 du1, okay, which gives us a half of e to the t squared. Right, that's the lower side. So we've got that there, okay? So we evaluated this, and we evaluated this here. Now remember, actually, on this point, this was integration by substitution, so I'm going to make another video on that. It's not too difficult, but it's just about finding the the right substitution to make. It's a bit easier than integration by parts, as I'm sure you know, but we'll make a separate video on that. So anyways, we got these things, right? So now we're just going to apply it. So uv minus the integral of v du. Okay, if we apply that, we've got t squared, okay, t squared, actually a half t squared, right? That's v, and then we got t squared. Yeah, we got half t squared times e to the t squared. Okay, and we can then say, okay, we're going to minus the integral of our v, okay, which is a half e to the t squared, times du, which is 2t dt. So what do we get? That's, well, a half t squared times e to the t squared minus t minus the integral, okay, of t squared dt, right? And from here we can just say, well, that's going to give us a half t squared e to the t squared, okay, minus a half e to the t squared plus c. So if we integrate this one by parts, we'll get to this, okay, as given up here, right? And that, guys, is going to be your answer when you can't integrate according to lie 8. Okay, you got to get a bit creative, but most of the time this will work, but there is an exception, such as in this case where that's not going to work for you. Alright guys, now that we've gone through the basic notion of integration by parts, and you know the common pitfall there, which is what to pick in order to integrate by parts, now we can go through what happens when we slip in a trigonometric function, specifically products and powers of trigonometric functions, because this is where a lot of people get mixed up and confused and problems start happening. So let's investigate the 4 scenarios that we can get when it comes to these trigonometric functions, and how exactly we're going to integrate using 4 strategies, or 3 strategies technically, in order to. Right, guys. Now, in the first scenario, okay, we're going off the assumption that we've got a integral like this, okay, cos to the power jx times sine to the power kx, okay, and scenario here is basically that k is odd, okay. So what would you do in a situation like this? If k is odd, what we need to do is we need to rewrite sine, okay. I'm going to rewrite sine as sine to the k x, okay, is going to equal sine k minus 1 x sine x. Now, don't stress if this looks a bit complicated, because all it is we're just kind of grounding on the theory here, right? And from here, we're gonna do an example, and then from here, from the sine kx, what we can say is we know that sine squared x, okay, is equal to 1 minus cos squared x, right? So therefore we can use this now to basically rewrite sine to k minus 1x in terms of cos x, okay? And then we're going to integrate using u is equal to cos x, okay, which means that du is going to equal minus sine x dx. Now this looks a bit complex, but we're going to go through an example and everything will be kind of simplified. Alright guys, so here we've got a very clear example where we've got k is odd, okay. So this toolbox, show you over there. Okay, here's k is odd, okay, which means what for us? First thing we're going to do is I'm going to say that the integral cos 8x sine 5x dx is going to equal the integral of cos to the power of 8x, okay, sine 4x sine x dx. Does this ring any bells? Okay, remember, we're applying this here first. We've broken up our sine to the power of kx into this format. Right, moving on. We're then going to say, well, this is then going to equal cos to 8x, okay. Then we're going to have sine squared x, right, and square, okay, because obviously that's what sine to the 4x is, okay. We'll times that by sine x dx. And why have we done that? We've done that because remember we're setting it up for this, okay. We're setting it up for this, so we're then going to get cos to the 8x, okay. Now applying our trig identities, we're going to have 1 minus cos squared x squared times sine x dx, okay. So we're then going to get cos to the 8x yeah, and what we can do from here is we can actually say we're going to say let u equal equal cos x, okay. So we're applying our next phase here. So if we let u equal cos x, we get that it equals u to the 8, 1 minus u squared, okay, and sine x dx, right, what does that equal? Well, sine x dx, negative du is equal to sine x dx. Okay, negative du is equal to sine x dx. So therefore, we can use that to say, well, we're going to have u to the 8 times 1 minus u squared to the square root, okay, times by minus du. Of course, remember this is an integral, so we've got that there. And then we can expand it. We can say that we're going to get from here, let's see, we're going to get minus u to the power of 8, okay, plus 2u to the power of 10, minus u to the 12, times du. And so it's just a case of now integrating. So very easy. We can just say, well, we're negative 1 over 9 u to the 9, okay, plus 2 over 11 u to the 11, minus 1 over 13 u to the 13, plus c. Now, we're not done yet. Since u is equal to cos x, right, we're going to get negative 1 over 9 cos to the 9x plus 2 over 11 cos to the 11x minus 1 over 13 cos to the 13x plus c. Okay. And that's going to be the final answer, guys. So as you can see, these steps seemed a little bit more, weird with that context. We've applied them here, right? So signs of the case, we've done that here. Okay, we rewrit it. Next, we used our identity of sine squared x. Okay, and then lastly we integrated using u substitution to get to this. Alright guys, now for scenario 2, we've got the situation where j is odd. Okay, so in this scenario where j is odd, i.e. the exponent of cos is odd, we're just going to do it the same as pretty much, very similar to the one before. So we're going to rewrite, firstly, cos to the jx. Okay, we're going to say that's equal to cos to the j minus 1 x times cos x. Okay, and then we're going to say we're going to use the identity. It's going to use cos squared x, okay, is equal to 1 minus sine squared x. Okay, similar to what we did before, just on the other side, and then integrate using u is equal to sine x. Okay, because this is going to give us du is equal to cos x dx. Okay, perfect. So without further ado, let's get an example going. Alright guys, quick example of when the exponent on the cos side is odd now. So what do we do? Well, we're going to say this. We're going to have cos squared x, cos x, sine squared x dx, okay, to start with. Because remember, step 1, okay, we're then going to use our trig identities. So we're going to say we then get 1 minus sine squared of x, okay, times that by cos x, and we've got sine squared x here again. Now, we're going to say, okay, let u equal sine x, okay, therefore, what do I get? Well, if I let u equal sine x, okay, in fact, let me just put that there, sine squared x, cos x dx, okay, because you'll see what happens now. If I let u equal sine x, that means du, okay, is equal to cos x dx, which is this, right? So if I let u equal sine x, what we get is the integral of 1 minus u squared, okay, times u squared times du, right? And so I get u squared minus u to the 4 du, right? And if we expand that even further, what we're going to get is, okay, u3 over 3, that's u5 over 5, right, and we can therefore say that that's just going to equal sine to the 3x over 3, okay, minus sine to the 5, x over 5 plus c, okay, and that's going to be the final answer for this one. So you can see it's actually fairly easy. All you have to do is remember this kind of algorithm and it becomes much more simple. But these are common pitfalls that people fall into a lot because they don't understand where to start, but now you do. Right, guys, so now what about scenario 3 where both are even? Okay, so when both are even, what we're going to do is the following. We're going to use these two things, okay? So we're going to say sine squared x is equal to 1 minus cos 2x over 2. I'm going to use cos squared x, okay, is equal to 1 plus cos 2x over 2. Okay, these are going to be the two identities that we're going to utilize if both are even. Okay, and once we've got these two identities, we are just going to basically reapply the other strategies 1 and 2 where appropriate. Okay, so let's get into an example to show that. Alright guys, so here we've got a example of this type of scenario. Okay, both are even. Why, you ask? Because I didn't see cos. Well, if you think about it, what we've got here is cos to the 0x. Okay, so two evens. And so with that, we can say the following, okay? We're going to say this is going to equal the integral of sine squared x squared dx, okay? And then what we're going to do is we're going to substitute in, okay, our formula that we just used before. Alright, but just to make things a bit more simple, I'm just going to use the other form of it. So I'm going to say we're going to get the integral of a half minus a half cos 2x, okay, squared dx. Right. So now we've got that bit. Now what we have to do is, well, expand it. So if we expand this, what do we get? Well, we're going to get a quarter minus a half cos 2x, okay, plus a quarter of cos squared 2x. Let me put the x there, right, and we can then go even further with this. All right, we're going to say I'm going to say that we can actually say this is going to equal quarter plus a half cos 2x plus a quarter half plus a half 4x. Okay. Dx. Now why have I done that? Why have I done that? Because if we go up here, right, we've just applied this in this scenario. Okay. So, and again, because over here we've got 4x, sorry, we've got 2x here, we're therefore going to have to, times it by 2, which gives us the 4. Right, and then now we can simplify this. So if we simplify this down, what we're going to get, we get 3 over 8 minus a half cos 2x, okay, plus an eighth cos 4x dx, okay, and then finally we just integrate it. So if we integrate this now, we get 3 over 8x, okay, minus a quarter sine 2x plus 1 over 32 sine 4x plus c. Okay, and that's going to be the final answer. So again, over here, this is the same as saying sine to the 4x times cos 0, cos to the power 0x. Okay, and we just follow the dots from before. Right, so from here. So remember, we can put this in as this. Okay, we expand, and then we recognize that this here is the equivocal here. We have to times by 2 to get 4x. And finally we integrate to get this answer. Okay. Lastly guys, if both are odd, right, all you have to do, okay, is apply the scenarios of either 1 or 2, either or. It doesn't make a big difference, and that will enable you to basically get the same kind of results. Okay, so remember, if both are odd, it doesn't make a difference. And that's basically it, guys. So I appreciate the you guys watching. That was it for this time. Okay, as a recap, we went through the entire quick thing, integration by parts. Okay, we went through Lie8. Okay, and we also did some trigonometric examples, and that's not all. We're going to have some more integration coming out soon, going through some just hard questions on integration by parts, but this is a good foundational block, at least one of the foundational blocks that's good to have. And yeah, I'll see you in the next one. Thanks guys.